All right, let us begin. We have a problem in circular motion, specifically vertical circular motion. This is problem number 63 on page 172. A pilot is flying in a circular motion. We have 4 critical points that I'm going to show a free body diagram of our pilot at each of those 4 critical points. What we're asked is if he's at this top point, the top point of his circle that he's making as he's flying in a circle, a vertical circle, hence vertical circular motion. If he doesn't feel the push of the seat on his body, and if he has a mass of 75 kilograms, and if his airspeed at that moment in time is 120 meters per second, what must be the radius of this circle that he's making in this sort of loop in the air? I encourage you before watching this video to attempt to solve this problem on your own. Of course, we already have our circle drawn. We just need to include here the forces that are acting on our pilot as he goes about the circle. There are 2 forces. On each of these points, there's always gravity pointing down. At each of these points, there is the force of gravity acting on our pilot, and in every circumstance, it has the same magnitude and direction because it's the same pilot, and we call that the pilot's weight. At 3 of these locations, there is the response of his body in the chair, so the chair pushing back on his body, and it's actually that force, the chair on his body, that keeps him in the circle. We call this as well a normal force. There's a normal force that's pushing up against him, and it's this force that pushes him towards the center of this circle. If that force did not exist, did not push towards the center, then we wouldn't have a centripetal force. If we don't have a centripetal force, then our pilot cannot remain in circular motion. There needs to be some centripetal or towards the center force to keep him in the circle, right? Or to keep his velocity constantly changing. That's what happens as an object travels around a circle. Its direction, the direction of its velocity, is constantly changing, despite the fact that the magnitude of the velocity or the speed is staying constant at 120 meters per second. The direction is changing, therefore the velocity is changing, therefore he's accelerating. So he needs a force to manage that acceleration. For these 3 circumstances here, at the bottom of the circle of this loop, at the sides of the loop, that force that keeps him in the circle is the normal force, the force of his chair on him. However, at the top of our loop here, we're told that the pilot no longer feels the force of the seat on his body. So he feels weightless. He feels as if he's, for that moment, that he's floating through the air, just as if you were falling through the air, maybe in an aircraft, and the plane suddenly had turbulence that caused you to fall, or caused the plane to dip down really quickly. You would feel weightless for a moment. You wouldn't feel the force of the chair on your body in the same way that our pilot here is not feeling the force of the chair on the body. And yet, he remains in this circular motion, despite the fact that this normal force is gone. That is because there is still a force oriented towards the center of the circle, and that is his weight. So now let's begin to analyze this problem. We have the net force for an object that's moving in circular motion. We need to look at what are those forces that are centripetal or pointing towards the center. We look at all of those forces specifically for this point, because that's the point that we're concerned with, the top of his motion. The only force that's oriented towards the center of this loop or this circle is his weight. That must be equal to his mass times his centripetal acceleration, which we know is equal to mass times v squared over r. We know his weight, the magnitude of his weight, is mass times gravity. That's how we define weight. That mass times gravity, that weight, is equal to mass times the velocity squared divided by r. So we can now take this equation. We see that the mass of our pilot does not actually matter. It does not matter what his mass is. What matters is instead what gravitational field is he in, what is the radius of the circle he is transcribing or negotiating, and then what is his velocity. Here we're asked to find what is the radius of this loop that he must be going on if he's traveling at this velocity and that's his mass. We find, if we rearrange this equation to solve for radius, we find that radius and gravity will switch spots. So the radius will be equal to v squared divided by g. We know his velocity, or the magnitude of his velocity, his speed, that is 120 meters per second, that quantity squared, divided by our gravitational constant, which is 9.80 meters per second squared. So we find that our radius is 120 squared divided by 9.80, with two significant figures, the 1 and the 2. The 1 and the 2. We find that the radius of this loop that he negotiates is 1,500 meters. 1,500 meters. If this loop were any smaller, then he actually would have a normal force that's generated on him. But at the radius of this loop, we find that he no longer feels the force of his seat pushing up against him. All he feels is his weight acting on him. Because he has nothing that he's pushing against to feel that weight, he feels weightless. All right, thank you.